welcome you all to the new video on theory of metal cutting. So this is our second class here in theory of metal cutting. Uh, so in the previous class we discussed about the fundamentals or what are the manufacturing process, the differences between what is manufacturing and what is production, and we've seen a few manufacturing processes also, category A, B, C, and D. That is shaping, forming, joining, and extrusion processes. Then two other processes also we saw. Those are material properties modification and the finishing or the surface exterior finishing processes. So they are value addition processes. So we saw the what is manufacturing and a few categories of manufacturing processes. So now we are getting into the depth of metal cutting. What is metal cutting and how it is being done? So we see the image here. So a common turning process is being done by a CNC machine is shown here. And similar is explained in a two-dimensional figure in the right side. So we have a workpiece. The workpiece is obstructed by a tool. Generally a tool should be much harder than the workpiece, right? So we are going to cut a paper using a metal knife. So we are going to cut the hard metal with much other harder metal. So few commonly harder metals are diamond, inconel, cubic boron nitride, CBN. So those are metals and commonly used metal in is titanium carbide. So carbide bitted tools, so those are used. So we are seeing here the image on the right side. So workpiece, a solid workpiece is obstructed by a tool, a much harder metal, so that we termed as a tool, and it is going to create a shearing force, shearing action on the workpiece. So we can see the shearing plane that has been erupted from the normal surface. So when the tool obstructs, a shearing action is being done, and we are creating a chip. So those chips are extruded or removed particles from the workpiece. So these chips are removed from the workpieces to they may be an unwanted or a extra material that is being present over the workpiece. So the shearing plane is shown here with a few categories, that is based on the shearing plane, the shearing force or the cutting force, the power, the temperature created, everything is being interpreted, or it is being changed or modified by changing the shearing plane. So here in the first image A and image B shows the difference, higher shear plane and a lower shear plane. So when higher shear plane is maintained, we can have smaller chips, and when a lower shear plane, then we will be having much larger chips. So when larger chips are formed, then obviously we must have higher cutting force. If we need to have higher cutting force, then the amount of power required for operating this object will be higher. So these are interdependent on each other. So the shearing plane or the shearing angle determines the power, the cutting force, everything. So we'll be generally maintaining a normal acute angle, such that a common cutting force or a shearing force can be used. So we have two different types of cutting. That is, one is orthogonal cutting and the other one is oblique cutting. So the first is orthogonal cutting. The basic, the orthogonal, the name itself, it means that the workpiece and the tool is kept at perpendicular. It is kept at a 90-degree angle, and it is a two-dimensional simplified process to form the chips. So the deformation zones involves a primary shear zone and a secondary shear zone. The chip flow follows a normal to the cutting edge. So in oblique cutting, it is other than will be having an acute angle. The tool will be kept at a certain angle with respect to the workpiece. So the angle between the tool and the workpiece determines the nature of cutting, the type of cutting. So this is three-dimensional process. We be having the metal removal process in 3 dimension, and the chip flows helically or in a side angle. So the chip does not obstruct or to interpret the workpiece. So we have shown here the figure shows a very clear picture of how the orthogonal cutting and the oblique cutting will be done. So a workpiece is kept, and the tool, the angle between the workpiece and the tool shows the nature of cutting, the orthogonal cutting and the oblique cutting. Cutting edge, the cutting edge is normal to the tool fed, and here the cutting edge is inclined at an angle. So it is inclined, it may be an acute or it may be an obtuse. The shear force acts on the larger area and the shear force acts as a smaller area. So when the shear force acts on larger area, then the type of chips formed will be larger, hence larger cutting forces or other parameters will be involved. So another table column shows the differences between the orthogonal cutting and the oblique cutting. The cutting angle, the flow of chip, the tool has a lesser cutting life. That is, in orthogonal cutting, we'll be having a perpendicular interruption between the workpiece and the tool. So the tool will be having lesser cutting life. It may be used, it can be used for over 100 cycles or much or lesser. And when compared to the oblique cutting, if the same tool and the same material and the same workpiece can be used in oblique cutting, it may go up to 120 or 150. So that is the amount of tool life. Then the shear forces acting per unit area is high. The surface finish, the cutting edge, and the components involved are the cutting forces are the parameters compared here when compared to orthogonal cutting and oblique cutting. And cutting, the type of cutting we've discussed. So classification of cutting tools we'll discuss in the next class. So this classification, I'll just give a small gist. That is, cutting tools may be classified based on the number of points or the cutting edges that is present. So single point cutting tool is a single shaft. Multi-point cutting tools is a multiple cutting edges will be present, and a solid versus tipped that is a solid edge or a tip. The point end alone will be hardened. Then indexable inserts. Some inserts can also be used for this process. So thank you all. We'll